I'm Salwa Mostafa, postdoctoral researcher at University of Oulu, Finland. I would like to present my work in collaboration with Nokia Bell Lab in Espoo, Finland about intent profiling and translation through emergent communication. Our agenda here, I will first give a brief introduction about intent-based networking and emergent communication, then introduce the motivation behind our work, introducing our system model, problem formulation, proposed framework, then present our simulation model and results and give a short conclusion about the work. First, 5G and beyond the networks are expected to support various services and applications like augmented virtual reality, cloud gaming, vehicular to everything, smart industry. All of these applications have different service demand and relying on traditional manual configuration and management for the network will not be applicable anymore or scalable with the number of applications expected to be supported in next generation. So network service providers are driven to move toward automated network and in service management. One of the good solutions for this was introducing intent-based networking, which provides simple and efficient automated way to configure and manage the network. It basically tries to understand what the network users or applications want and what the network operators can offer and try to optimize the network operations with service needs. One of the technologies also that facilitates implementing IPAN is introducing network slicing to the network, where the network operators can manage the network capabilities in a more efficient way, as network slices can provide or create multiple end-to-end logical network to share physical and virtual infrastructure. So to talk more about intent-based networking, first, like intent has been defined as a high-level abstract description to the network services, and it has a complete life cycle, which takes over 5 steps. The first one is intent profiling, where the users or the application interact with the network, express what they want or expected as a service or outcome from the network. Then it comes the network translation, where the network receives the intent from the application and converts it to network policy or low-level configuration to different functions and devices in the network. Then we have network resolution, where we try to solve any conflict between independent intents submitted to the network. The network activation, where we activate the functions and services to provide the intent requested by different applications. Then it comes a network assurance, which indicates the success of the deployment for the intent during the life cycle, from the start of the service till the end. Of course, the network capabilities and are managed and configured from shared physical and virtual infrastructure to reduce the cost for the operation network and facilitate efficient utilization to the network resources. So since for our work, we focus on the first 2 phases of the intent-based networking life cycle, is intensive profiling and intent translation. We will talk more about the literature, the state of the art for each one of them, and what we considered later on in our work. So first, about intent profiling, as we know, like IETF has classified the intent profiling based on the intent type, intent scope, and the network scope. If the network is edge network, cloud network, and the intent is requesting web applications or requested security services. Based on this domain, they can try to manage how they can implement the requested intent. So so far in the state of the art, there was some studies proposed human-friendly interfaces, GUI interfaces, or drop-down menu template to the network users to choose some requested services based on what they want. But unfortunately, this method may not support new applications come up in the network, and some requested services not listed as an option in this drop-down menu or template. So later on, some studies proposed to use natural language processing, where the network users can express in a human language what they want or expect from the network, and then the network later in the translation step interpret and interpret these intents to a network configuration. However, NLP is not like so successful or so accurate, as there is many specific grammar formats needs to be considered and to detect the important information. And if the user's input is too fake or not accurate, it will be hard for the network later on to translate to the appropriate configuration. So later on, some studies also specified more domain-specific language where the users can express in a more readable technical details to the network what they expect. But also, this method was not practical or available for all users if they don't have background about the technical terms from the network, and it requires that the users have some knowledge about it, which is not general enough for all types of applications. This is for the intent profiling. So when we move on the intent translation, so also some studies has been proposed to use template blueprint-based configuration files to support or activate the network devices and services to the network, but usually due to the various demands of services in applications, it may not be efficient in utilizing the network resources and handling multiple intents submitted to the network at the same time. So later on, network service descriptors, translators has been introduced, where they contain some deploy templates to directly used by the orchestrator to support the network devices, and also some studies proposed keyword-based translation, where they can detect the associated words in each intent and map it to network configuration or policy. So far from the literature, all this traditional mapping and the translation scheme is not so accurate and can guarantee the service requested by different applications in the intent. So there is still a big gap to improve these two stages in the intent-based networking, and it still needs further investigation. So it comes here, as we can see, most of the aforementioned work before focus on human-to-machine scenarios, where they assume that the users have like graphical user interfaces or drop-down menus they can interact with the network. Not too much attention has been paid to machine-to-machine communication. For examples, in a factory scenario where some robots or non-human machines try to interact. Some machines try to interact with the network. they require to come up with their own, they need to come with their own common language, non-verbal, to express their intent to the network, which may not be quite difficult in the environment to set up this kind of common language. So and also in the existing literature, they assume that the intent can be easily expressed as a network quality of service to different applications. So this may not suitable as the applications needs to interact with the network based on their domain language. For example, some applications require security, some applications require web services, some others require computing, more computing resources. Each of them has his own language to express like the intent for the network. For the network to understand all these different domains based on the application is quite complex and may not be practical or scalable. And also using a predefined list of generic intents that can activate the network services may not be suitable for future network capabilities to efficiently utilize it with the huge number of applications coming up. So so in this work, we introduce a framework based on emergent communication for intent profiling, where each of the application can express their quality of experience or quality of service to the network through emergent communication messages. What we mean by emergent communication is that these messages has no predefined meaning before. And when the users or the applications interact with the network, they learn to associate these networks to these messages to network capabilities based on their needs. And later on, the network can map it further to appropriate network configuration. So if you are not so familiar with emergent communication has been evolved as a research field motivated by human intelligence, which we rely on communication and use language to interact in complex social situations. So in the same way, they want the deep neural agents to learn their own language to achieve certain tasks in a cooperative way through getting involved with or cooperate in a communication game where they get some feedback and reward to learn the meaning associated with these messages, and then come up with their own language based on the environment they interact in or the task they try to solve. So the formal definition for emergent communication is as the field wherein the agent with no pre-existence communication protocol interact with the goal of to bootstrap communication protocols that act as a shared language between them to achieve a specific task. So motivated by this, we see that emergent communication has some potential for solving the situation where machine-to-machine communication scenario. So here we will introduce our system model. We consider a system model consists of a base station or a network, has network slices with different capabilities, computing, caching, communication. And we have in IIoT mobile devices, each of them run its own application and generate an intent with a specific quality of experience to the network. Then we convert this quality of experience to quality of service to judge if the intent can be satisfied by the network or not. Can be, for example, for our specific scenario, we express it as a deadline for communication and computation. And the network or the base station is responsible for assigning network slices with different capabilities to satisfy the requested service by different applications. So based on the allocated slice, network slice, we can compute the uplink time and the computation time to the network and compare it with the quality of service requested by the users and see if it was successful in allocating the resources to the users or not. So to solve our problem, which is intent profiling and the translation from different application to the network, we divide the problem into two subproblems. First, about the intent profiling, we want the network users or applications learn how to associate their different applications with some communication messages. And based on the generated instance of the intent, they choose from a set of vocabulary how to do it. And this is done by optimizing a mapping function that maximizes the association between the number of intents and communication messages. Then for the intent translation problem, after the user sent these messages to the network tried to learn how to associate these messages with network configuration. So the network configuration, in our use case, we simplified it and assume that there is some pre-configured network slices available for these applications in the network, and the network needs to learn a mapping function between these communication messages and the network services. And the objective is to maximize the number of successful association between messages and network slices. Our main objective is to satisfy the number of successful association between intents and the network slices. So we have the users have different intent with different instance, and they want to be successful intent deployment by getting the appropriate allocation for the slices from the network. This is a general optimization problem for our problem. This objective can also be achieved by maximizing the two objective functions we stated here by optimizing the mapping function for the intent profiling and the mapping function for the intent translation. However, unfortunately, these mapping functions are unknown and hard to model explicitly mathematically. So we proposed an AI framework to approximate and solve the problem. So we proposed an AI framework based on cooperative multi-agent RL, where the network and IoT mobile devices or applications in the network act as reinforcement learning agents. They adopt emergent communication technology to learn a communication protocol that can ground these communication messages between the agent and the network. So our proposed framework, just as in traditional reinforcement learning, we have the environment and we have the network allocates network slices, and the applications generate instant of intents and they exchange messages with the network and try to interact in the environment through taking some actions, get feedback about the current state, and then receive a reward from the environment to learn how to choose appropriate actions. So for multi-agent RL, it's usually described as a decentralized, partially observable Markov decision process where we have a state space expressing the state of the network, observation in action space, and we have a transition function that maps the states and actions to a probability distribution, and a reward function that maps the state and action to a specific real number where the agent can learn through this reward which actions give a successful reward or higher reward. They interact over a certain period of time and take actions based on this current state and observation. So to be more clear what is the state space and what is the action space, what is the reward in our framework for the network, we have we stored the L. It can be 3 or 4 previous steps about the uplink and downlink communication messages received from the agent and sent from the network and the environment action. So we have here the uplink messages, the downlink messages, and the environment action for L steps to learn from the history. And for the IoT mobile devices, they also have L uplink and downlink communication messages and the generated intent as a state. For the network, the environment action represents the network slice allocation to each IoT mobile devices, and the communication action takes into direction uplink and downlink. For the uplink, the IoT mobile devices, it choose one of the set of communication messages to send to the network based on their generated instant of the application, and the network sent later on message 0 or 1 to indicate the success of the failure of the network slice allocation from the network. Then we have the reward is positive if the intent is satisfied based on this allocation, and negative otherwise. And then we have the team reward because we want them to have a common communication protocol. Again, these communication messages has no predefined meaning, and this meaning emerges through communication. They learn based on we train the neural network to learn these communication messages. It takes as an input the state space, and then it optimizes the network, minimizing the loss function and adjusts the weight until it gives a distribution over the output to choose which messages is appropriate for which application. To solve the decentralized partially observable Markov decision problem, we adopt one of the famous algorithms in multi-agent RL, which is multi-agent proximal accuracy optimization. For our simulation model, we consider the warehousing logistic area where we have a network and 5 IoT mobile devices. The network has 10 network slices with different capabilities, and we stick with 2 applications: ultra-reliable low latency communication and enhanced mobile broadband to simplify our use case. And then we have the uplink communication messages equal to the number of network slices, so the users can learn to associate their application to the appropriate network slices. We compare our proposed framework with some baselines, like the perfect knowledge, where we assume that the network checked all possible options of the network slices and choose the one that can guarantee the quality of experience. And we have the random assignment, where the network allocates random slices to IoT mobile devices. And then we have self-learning or slice selection, where the IoT mobile devices learn in their own through interaction with the network how to associate their applications to network slices with no previous communication or with the network. Here we have like our simulation model for our system and the hyperparameters for the MAPPO algorithm. Here we can see our simulation results, which, as we can see, our proposed scheme, the green one, gives a very close performance to the perfect knowledge benchmark and outperform the random assignment and self-learning. Both in training and testing, it also gives a very close performance to perfect knowledge. Also, when we normalize them, see the failure quality of service, as we can see, it's decreasing, and it also gives a very close performance to the perfect knowledge framework during the testing. Afterwards, we try to investigate the behavior of our proposed algorithm or propose a framework when we increase the number of users in the system. As we can see, it still gives a very close performance to the perfect knowledge. But when the number of users increase, the gap started to decrease because there is larger number of messages, and we need to use larger neural network to scale up in the network. But here I just use the same network for all number of users. Also, we can see here as failed quality of service translation. As we can see, random assignments gives really poor performance when we scale up. So in summary, we have investigated the problem of intent profiling and translation in intent-based networking, where we focus on machine-to-machine scenario, and introduced emergent communication along with machine learning as a solution or a framework. For IoT mobile devices, they learn a policy to map their intent to communication messages to the network, and the network learn a policy to translate these communication messages to network slices. As we can see from the simulation results, it's a proposed scheme outperform the perfect knowledge base benchmark, and it also outperform random assignment and self-learning strategy during training and testing. So this work has been already accepted in ICC 2024 and available on arXiv. Thanks.